Here we're going to look at sampling distributions of proportions. In the past, we formed the sampling distribution of sample means, or the SDSM, by repeatedly taking samples of size n from a population, then plotting the sample mean, x bar, of each sample. For that SDSM, the mean of the sample means, so mu sub x bar, equals mu. So the mean of the sample means was the mean of the original. The variance of the sample means is sigma squared over n. And then the standard deviation was the square root of that variance. Now I want to point out that the variance of a population is just sigma squared. When you divide by the n, you can think about that as taking an average variance. The theory of sampling proportions is very similar to when we construct the SDSM. However, now instead of calculating sample means, x bar, we calculate sample proportions, p hat. So this symbol with the little mark above it, we pronounce that as p hat. Okay, and again, the idea is rather than calculating a sample mean, we're going to calculate a sample proportion for every sample that we take. So rather than getting a mean, like a sample mean of like 2.7 miles, we're going to get a proportion such as 0.38. Now remember, proportions you can also think about as percentages. So a proportion of 0.38 would be 38%. Okay, so when you see the word proportion, you can think about how it's related to percentages. So how do we find p hat? It's the number of successes divided by the number in the sample. Okay, so x over n. So if we take a sample of, say, 100 people, and we had 40 successes, p hat for that sample will be 40 over 100. Okay, so it's very easy to calculate. We have seen proportions before when we work with the binomial distribution. Recall that p is the probability of success in the population, and 1 minus p, q, is the probability of a failure in the population. Okay, so with a binomial, there are two possibilities. We have success and a failure. And the mean and standard deviation for any binomial situation, this goes back to formulas you used before. The mean equals n times p, so your sample size times the probability of success. And then the standard deviation is the square root of np times 1 minus p. And sometimes I'll write that as square root of npq. Okay, so suppose 30% of students who graduate from CCC have passed the A statistics class. If a sample of 100 CCC graduates is chosen, what is the mean and standard deviation for the number of students who have passed the statistics class? So the mean is just your sample size times the probability of success. So 100 times 0.3. So we would expect 30 out of those 100. Okay, so mu equals 30 to have passed the stats class. And then the standard deviation, substitute your numbers for np and qn, and you get about 4.58. So the sampling distribution of a sample proportion. If repeated samples of size n are taken from a population of values for a categorical variable, where the proportion in the category of interest is p, then the mean of all sample proportions, p hat, is the population proportion, p. If n times p is greater than or equal to 5 and n times q greater than or equal to 5, then the sampling distribution of p hat is approximately normal. Now sometimes you will see some people define that to be np greater than or equal to 10 and nq greater than or equal to 10. But many books and authors will also use 5. That's just basically saying you have a large enough sample size and you can assume that you have a normal distribution. Okay, so what that's saying is the mean of the sample proportions equals P, which is the population proportion. And the standard deviation of the p-hat distribution, so the standard deviation of the sample proportions, is the original standard deviation, square root of NPQ, which is coming from up here, divided by n. Now, believe it or not, what that simplifies to is the square root of p times q over n. And where that comes from, if we just look at the square root of NPQ divided by n, okay, looking at a square root of n divided by n, so just looking at that piece of it, well, that will actually simplify if we just look at that piece of it. N to the 1/2, because so square root of n is a 1/2 exponent divided by n to the first. Okay, and then if you subtract the exponents, because you have n to the 1/2 over n to the first, subtract the exponents, you get n to the negative 1/2. Well, a 1/2 exponent is a square root. The negative will put it in the denominator, so we get 1 over the square root of n. So what that means is the n in the numerator is gone, and then the square root of n gets brought into the denominator. Well, the way you can do that is just put the whole fraction under the square root. Okay, so the standard deviation is the square root of p times q over n. Okay, so that whole piece is under the square root. If you didn't follow that explanation, that's okay. Just know that that's what the standard deviation is for the sample proportions. And this is similar to the idea that the mean of the sample means equals the mean of the original. And the standard deviation of the sample means is the standard deviation of the original over the square root of n. Okay, so this was with the SDSM, and now we're looking at the SDSP. So instead of sample means, we're looking at sample proportions. Okay? But the concept is still the same. Okay, so to get a quick example of this, okay, so that same idea, the 30% of students pass the SAS class, you take samples of size, you repeatedly take samples of size 100 to form a sampling distribution of sample proportions. Okay, so the mean of those sample proportions will be 0.3, and the standard deviation will be the square root of p times q, so 0.3 times 0.7 over n. So that's about 0.0458. You can also think about this as the mean being 30% and the standard deviation 4.58%. Okay, so that distribution would look like this. So the p-hat distribution would have 0.30 in the center, and then if you add one standard deviation to that mean, you get 0.3458. The second standard deviation, so add 0.0458 again, you get 0.3916 and so on. Okay, so the concept is still the same. You have the mean in the center and the standard deviation. You can add and subtract that from the mean to get your axes labeled for the p-hat distribution. Okay, now in part A, it asks us to find the probability that p-hat is less than 0.27. So what we need to do now that we have a normal curve, we need to convert p-hat into a z-score. Okay, and the way you always do that is you take your sample statistic p-hat minus the mean for the population p divided by the standard deviation of p-hat. And remember, this is the same idea as z equals x bar minus mu over sigma sub x bar. It's the same concept, except now we're dealing with p-hats instead of x bars. Okay, so when you do this, p-hat is 0.27, p is 0.3, and then the standard deviation is your square root of 0.3 times 0.7 over 100. Now, I rounded up here, 0.0458, just like I would have if we had the standard deviation of the x-bar distribution. But when you calculate the z-score for it, you don't want to round too much until you get to the final step. So put that all in your calculator the way it is, and you should be getting a z-value or a z-score of about negative 0.65. And if you look at the distribution, 0.27 is between 0.2542 and 0.30. So it's going to be somewhere in here, which is between 0 and negative 1 for the z-score. So that negative 0.65 should make sense. So then you go to your z-table, look up negative 0.65, and you'll get 0.2578. So negative 0.65 is right here, 2578. Okay, and if we looked at that on the z-axis, negative 0.65 is where our sample proportion of 0.27 is. 0.3 is in the center, so that's a z-score of 0. So this area out here to the left is 0.2578.